concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. Woo! That's a mouthful, and we're going to have like 3 or 4 paragraphs that are mouthfuls, but I want you to just add something to your notes, and I probably already wrote it maybe, and it's the saying, add away, take away, I stay. Did we already write that?
No.
I saw.
Talked about it.
We talked about it, but I didn't write it.
You should write it.
Add away, take away, I say.
You should be familiar with that, me.
Huh?
Remember?
I remember talking about it, but I didn't write it down.
All right. So this thing will help you. Yeah, it will help and apply to concentrations and heat. When we talk about the 3 ways to disturb the force, these are 2 of them. All right. So this is really wordy, but we'll work through it. This is whatever. It's a great way. Changing the concentration of a chemical will shift the equilibrium to the side that would reduce the change in concentration. Which means if I add concentration, it will go to the other side to decrease what I just added. Or if I take away from one side, it'll go towards that same side to adjust the concentration back to what it was. Hello. Hayden Adams.
Come with me.
Have fun team.
Oh boy.
Lily looks
Appreciate
nervous.
it. And I just peed before this class too.
Some Mountain Dew.
I don't be saying something.
Okay, have fun, kids. Go fight me. All right. Did you see that group of kids?
It's like a bunch of dupes.
That those kids are gonna pass. That's funny. Hayden Adams. What if he comes back, tests positive for steroids?
Something went wrong.
I'm pretty sure.
Maybe he goes steroids.
All right. Anyway, shh. Look at the screen and shut your mouth. The chemical system will attempt to, you haven't looked at the screen or shut your mouth yet. There you go. The chemical system will attempt to partially oppose the change effected to the original state of equilibrium. In turn, the rate of reaction, extent, and yield of products will be altered corresponding to the impact of the system. Woo! That's fun. Hey, that all boils down to add away, take away, I stay. All right? Because if we have this simple reaction, let's do this here. It'll make more sense. So, all we're saying, when I change concentrations, it's as though I'm adding stuff. So if I add A, then B and A will have more opportunities to collide, which means they'll start to produce more of A and B. But what would happen to B? It would have to go down. Okay? So if I add to one side, I go away, which means I produce more of the other. As this top sentence says, changing the concentration of a chemical will shift the equilibrium to the side that would reduce the change in concentration. So my change was adding. In order to reduce my concentration, I have to produce more AB. All right. Since I said it, I'm going to assume you guys learned it perfectly. Did we talk about this graph?
Yeah.
This graph explains add away, take, I stay as well. It explains everything we just barely said. So we had these 3 chemicals at equilibrium in the Haber, whatever you want to call it, process. And their concentrations were not changing. I come along and I add H2 to the system. So it spikes. So H2 plus N2 goes to NH3. Don't worry about balancing it. But I'm adding to this side, which means what happens to NH3? It must go up to oppose this and to make it go down. So what has to happen to N2? It has to go down. Now look at the graph. Does NH3 go up? The answer is yes. Does N2 go down? Yes, and now a new equilibrium position is established. Okay? They're still flat, but they're at different partial pressures. All right, next. The effect of temperature. It's really simple. As long as you treat heat as part of the reaction, it's going to be just dandy. So here we go. The effect of changing the temperature in the equilibrium can be made clear by the following two things. A, you have to incorporate heat as either a reactant or a product. All right, so you're going to write it in the actual reaction. And then B, this is really important that you grasp this, assuming that an increase in temperature increases the heat content of a system. So when we're talking about adding heat, we don't add heat to one side or the other. We're heating the container that the reaction's happening in. Are we all right with that? So the overall, when we add, it's an addition to heat of the entire system. All right. When the reaction is exothermic, that means delta H is negative. That puts energy out, which means heat is included as a product. And when the reaction is endothermic, delta H is positive or takes energy in. Heat is included as a reactant. Hence, whether increasing or decreasing the temperature would favor the forward or the reverse reaction can be determined by applying the same principles as with concentration changes. What's our mnemonic? Can't say that word. It's add away, take away, I stay. So what that means, if I add heat, I shift away from the heat term, which is the word heat. If I take away heat, I stay on the same side as the heat term. Add, away, take away, I stay. Maybe one of the worst I's I've ever written. All right, now, most of the time in this class, it doesn't just say the word heat, it gives you the reaction in this format. Let me get rid of this. So it'll just tell you what delta H is. And I would hope that you're smart enough by now to know that delta H equaling a negative sign means what? Exothermic, which now means it's a product. Delta H equals positive, it's endo, and now that means that heat is a reactant. Is that rain? Wow. Moisture. I didn't even think it rained and snowed or anything in Utah anymore. All right.
Saturday now.
It did? No wonder my windows were dirty. All right. So since this is negative, for Le Chatelier's principle purposes, we would write it like this, where heat is written as a product. And then we apply our little saying. So look, if I add heat to the whole system, that's fire. All right, if I add heat, I go away from the heat, so I would produce more reactants. All right? If I cool it, then I'm removing heat. And now, hold on. We'll drop it in ice cubes. These are ice cubes. Don't worry about my drawing skills. All right, so now I'm cooling it. And what would we expect to happen if I decrease the temperature or I take heat away? It shifts towards the same side I removed from, so I would produce more products. All right, I'm feeling great about this. I assume you do too. All right, next are changes in pressure. Now, make sure pressure will only affect an equilibrium with an unequal number of moles of reactants and products, and this should actually say of gas. gaseous. So it's important for you to first realize that you need to have gases, or at least one. You have to have at least one gas somewhere for this to matter. And then you have to have unequal number of moles. Now be careful, we're talking about the moles as far as the coefficients are concerned, not moles as in it told you you had 0.3 moles of this and 0.2 moles of that. Okay, we're talking about unequal number of moles in the coefficients. So this is our classic friend, the Haber process. All right, it certainly has unequal number of moles. There's a 1 here, so 4 moles and 2 moles. All right, in order for you to understand this, you need to know that, and you should know this, moles occupy space. They require room to exist. Are you okay with that? In fact, we're going to say that a mole occupies 22.4 moles, or sorry, liters. Need to get rid of that. Now, that is at standard temperature and pressure, but roughly. So this side of this reaction would occupy roughly 89.6 liters of volume, right? This one over here would just occupy 44.8. It's really easy to notice that the left side requires more space to exist than the right side. Are we okay with that little nugget of information? All right, so keep that kind of in your mind. Moles occupy space. And let's see. An increase in pressure will shift the equilibrium to the side with the least number of moles. Now, an increase in pressure is generally the way that it happens is really a decrease in volume. Okay, so we're like pushing the piston down. It decreases the volume, so the pressure has to go up. Are you okay with that? All right. If you decrease the volume, and you had, I can't remember, 88 on the left, right? Or 89. All right. So I'm decreasing the volume by increasing the pressure. So if I have less space, then I'm going to favor the side that takes less space.
Is it because they touch each other more then? Or is it because the...
Not necessarily. All right. Now, the side that has more then will decrease, and the side that has less space, it will start to produce more of that. Now over here, a decrease in pressure will shift the equilibrium to the side with the greater number of moles. Because a decrease in pressure means an increase in volume. Now there's more room, so the thing that required more will increase, and the thing that required less space will decrease. We all right so far? We're going to apply this. All right, so I would highly recommend, if you're a note taker, to write all this in your notes. Let me get rid of that. That was too much of a help. So I have A, B, C, let's see, 7 things, and I'm asking the same question. Make sure you understand the question before you write anything. I'm asking, is that fun?
So good.
I'll bet. All right, so what we're asking, I'm telling you what I'm going to do to the system. You're going to tell me whether what I do makes more products or makes more reactants. You with me? I'm asking, does it make more products based on this change, or does it make more reactants based on this change? Okay, take about 2 minutes, maybe 3 or 4. Do it, then discuss, and see if you can figure this out. All right, we're going to go over all of them together. Okay. So make sure these click so that you can pass this part of the test, which is on Wednesday. Right, Ming?
Yes.
All right, good answer. Okay, so we have this process. It is exothermic. That will become important soon. So in A, we are increasing the concentration of O2, which means that the equilibrium shifts to produce more products. All right, increasing the pressure would shift to the side with the fewer number of moles, so 2 would be over here. So we would say product. All right. I'm 2 for 2, by the way, of ending my P line right here on the actual line itself. So, like, I'm on fire right now. Decreasing in temperature, so I'm removing heat.
So stay.
Oh, I stay to that same side, so I would produce products. This could be a special day. All right, increasing SO3. So now I'm increasing. The equilibrium will fight to reduce that increase by producing more of this stuff. So that would be reactants. Oh, I screwed up.
Go back, do it again.
I could do it. You're right. You're right. Okay. Feeling it. All right. Now, decreasing S. So if I take away I stay, what side is stay? Well, that would be the reactants as well. Letter F, decreasing pressure will shift to the side with more moles of gas. So that's the side with 5 versus 2. So we would say that goes towards reactant as well. Now, letter G, I've already asked, but we stress it in a different way. If I decrease the volume, this really means I'm increasing the pressure, correct? All right, if I increase pressure, once again, I go to the side with a smaller number, so that will be products. Okay, raise your hands if you got all of those right.
Wait, all of them?
Yes.
That's the one.
Okay, that's most of you. All right, now we're going to make it a little bit harder. It's not that much harder, but I mean, it's the same questions-ish. But we throw in a little bit more chemistry terms. So give these 4 questions. It says to predict and explain what will happen to whatever it's asking you. Take a couple minutes and work through those.
Hey, Bailey.
All right, let's talk through these quick, and then we'll do one last thing, and then we'll do math, because everybody loves math. You don't hate it? Or you do hate it? Okay. Thank you. All right, so we have this stuff happening. Let's see what happens. The effect in A. What's the effect on NH3? So we're going to define it by what happens to this. When additional solid is added. So if I add, I go away. Going away means I produce more of the other side, correct? So NH3 would do what? It would increase. Are we all right with that? The explanation why is because you would say something like, If additional reactants are added, more products will be formed. Right? That's not super difficult. I hope. Who had A correct? Raise your hands. You're amazing individuals. B, the effect on the equilibrium partial pressure of NH3 when additional H2S is added. I apologize for the word solid. So I'm adding more of this, add away. So that means this goes up, but what must have happened to NH3? It has to go down. Okay, letter C. Now we're talking about NH4HS. So what's the effect on the mass of this present when the volume of the container is decreased? Volume of the container is decreased is another way of saying what? That means pressure goes up, right? So if pressure goes up, I go to the side with fewer number of moles of gas, which is 0 over here, right? Versus 2 over here. So I shift towards the 0, or it increases. Yeah,
What if the
Bailey.
volume was decreased enough for there not to be enough room in the solid? Does
Say
make
that
sense?
one more time.
So if the volume was decreased enough that in its solid form there wasn't enough room for like the NH4.
So like super compressed,
Yeah, like super compressed.
we would
it
never do that.
It blows.
Yeah, it would blow up.
just, so it'd blow up? Okay, I'm just curious.
All right, now, so we're going to define what's happening to this one more time. The effect of the mass of that when temperature is increased. Okay, I got to look up here. If it's a positive sign, where do I write the word heat? On the left. All right, so if I increase, I go away from the heat, correct? Which means I move that direction or produce more products, which means what happens to this then? It has to go down. Okay, how many got 4 for 4 right there? Raise your hands. Okay. All right.
Now, what was it to be?
To D,
Yeah.
it decreases.
The solid mass of what?
This solid mass will decrease in part D.
Okay.
All right, last little nugget of information here. We're talking about a catalyst and its effect on the equilibrium. A catalyst increases the rate of both the forward and reverse reactions. So if both things are affected, how do you think this affects equilibrium?
Faster.
All right, it gets there faster, but what about the math?
It's still a ratio system.
It's still a ratio, so it's exactly the same. Good answer. Equilibrium is achieved faster, but the equilibrium composition remains unaltered. Okay, so like on our graph, when it goes flat, all that would happen is this would just happen farther over here. Those are no. That was supposed to be right on. There, that's a little better. Okay, worst things ever of my life, ignore those, but the lines will just go flatter faster, but they'll be flatter in the same spot. All right, now, this is to help you get ready for the test. This is a question off of an AP test in 19-something. It's a really good question, and I want you to work on it for 10 minutes. I will give you a hint on part A, because no one really got part A at first, last hour. So, it says all that, sodium, whatever. Then it says a sample of 100 grams of that was placed in a, whatever, it's rigid, meaning it won't change. Some of the original solid remained, and the total pressure was 7.76 atm when equilibrium was reached. Calculate the number of moles of H2O gas when present. All right, here's what you need to know. There's a 1 right here and a 1 right here, right? So what can we say about their moles at equilibrium? They're the same. So that would mean what about this number? How much of this number is water? not 1/3 of it,
Oh, I'll get it.
1/2, and that would be the other half. Are you okay with that? So half of 7.76 is water. Just on that hint, you can do the rest, I'm pretty sure. Nobody last hour got D right, but we kind of ran out of time anyway. So give that a shot. I'll tell you right now that the molar mass of sodium hydrogen carbonate is 84 grams per mole, just to save you 30 seconds. All right, so the audio's different because the other thing crashed. Let's do this together. How many have .545 for this answer? Raise your hands.
Yeah. Facts. 0.547.
Okay, well, whatever.
376.
I apologize for being off 2,000. All right, now, stick with me, friends. Don't break his glasses.
Shut up.
All you had to do was take this and divide it in half and then plug it into Pivner.
You kidding me?
I charged it by the moles of
NaHCO3.
Why?
I don't know.
I don't know either.
I would think so.
All right, now,
That's scary.
part B. How many grams of the original solid remain in the container under conditions described in this? Did anyone put 91? Because they're wrong.
Someone put 91%?
Lots of people do.
Wow.
Why would you put 91? Because they forgot the last step. 91 is the grams that are used up. And it's 91 point something. But so you should end up with like 8.7.
How do you
8.3?
end up with that? 'Cause I don't
I'm going to show you. Now, there are multiple ways to do this. Follow my logic here. This is the amount of moles of H2O, correct?
Yes. Yes, sir.
And there's a 1 right here, and there's a 2 right here, which means for every one of these, 2 of these were consumed. So I just take this number and I multiply it by 2. And you get 0.91, is that right? No, sorry, 0.11, 0.109. 1.09 is what I'm trying to say. Are we good now? That's what I.
Wait.
That's just this number times 2.
Yeah. Oh, yeah, the 1.1.
All right, now that is the moles of NaHCO3. But I need to know its grams, so I multiply for every 84 grams, I have 1 mole. So that's why I told you that number to start with. And you end up with 91-ish. And that's the amount used up. You with me? All right, how many did I have to start with? I had 100, so and it was ish, so we just subtract, and you said 8.3 is really the right answer?
So for number A, you can just ignore the 100 grams.
100% ignore it. It's okay. Who understands the logic behind how we just did that now? Who had 8.3 in the first place? Raise your hands. Who?
I'll tell you what I did in accident. I stopped at the, I don't know why I stopped at this, but I got those 1.1 moles of the NaHCO3 and I stopped there for some reason.
Then you got stuck on dividing by 5 and all sorts of lost business, maybe?
Yeah, the next part.
All right. Part C is a lot easier than everyone made it last hour. KP, we don't include this solid or that solid, so we just put KP equals, did you mess that up?
No.
But it's not the constraint, it's the partial pressure.
Okay,
effect.
well, brackets then, I'm sorry.
Yeah.
So now we just substitute these values in at equilibrium, and how do I know those values?
There's 7.76.
They're half of that number, right?
Yeah, it's like 15-ish. Yeah, 15.
15-ish, sounds good to me. Hey, is this product or reactant favored?
Oh,
Product. Why is it product favored? Okay, and how about in a KP explanation? Because KP is significantly greater than 1. All right, letter D.
I'm confused.
Yeah, where are you confused?
3.8 times 3.8.
It just does.
So I got the same system.
Right, 3.88 times 3.88.
Yeah.
You added.
Yes. Oh, sorry, I meant, oh, maybe. 3.8 times 3.8. That's weird. Never mind. Carry on.
I'm all about that. Okay. In letter D, maybe a trick question, maybe not, but what would the total pressure at equilibrium been? The same. Why would it not change?
Because it never does change.
This one over here already proved we had excess, didn't it? At equilibrium, not 100 grams will break down. So if I add 110, oh hey, still 100 didn't even break down. So we're just going to have more excess solid, but is solid in the expression. Or I shouldn't say that. Does solid have anything to do with the gases? Not
I
really.
don't understand, because it's like the same thing of like you're adding the concentration to the reactant side. Wouldn't that increase the product side?
In a way, except for we've reached a state where no more of this will break down. It would only have worked if when we got to 100 it had all broken down. But we've saturated the system, so to say. It won't hold any more than it already held at 7.76 halves.
It's just because it's not got something else to react with.
That has a lot to do with why it won't react.
So if it's just something decomposing, there's only a certain point it can get.
Yeah, and that has to do with saturation, which is something we've talked about with solutions, but it can certainly happen here. This container, whatever it is, at these conditions are only going to allow 0.547 moles to even be decomposed. Anything more than that, it will just stay as a solid. Yes.
My question is how, like, adding more solid doesn't increase pressure because it still takes more space, and so it decreases the space.
Okay, well, now,
That doesn't make
you're right, but when we talk about adding a solid, and they'll say this, it'll say assume no change in volume. Adding 10 grams of a solid is not going to change the volume significantly. Well, if it said add 5 pounds, yeah, but they're not going to, and they'll say that. They'll be very specific. It usually says assume volume.
I wonder why. React.
Are we okay with this style of question?
Yeah.
If you want any more explanation, this is on the big idea worksheet that's on there that you don't have to do, but might help you. Have the answers. Okay, tomorrow we review a few more